Excuse me. Thank you. Okay, so let's shh. So first thing we have to do is figure out which substitution is appropriate. So we have 25 minus x squared. So which one do we use? Asia, what do we use? Sine. Yes. So Asia says the sine, which is correct, which I knew she had the right answer because I looked at her paper. So you're going to create your triangle. Your right triangle. So that's your angle theta. So if we're going to use the sine, it's going to be the sine of theta is x divided by 5 because this is 5, the square root of 5, and this is the square root of x squared. So that means the opposite side is x. The hypotenuse is 5, and that's why we chose the sine, so that the third side would be 25 minus x squared. We could have used the cosine, but there's no advantage to using the cosine over the sine, so we're just going to stick with the sine. So you're going to calculate. So remember, you're going to. We'll give you a little help here. So you're going to get x. You're going to calculate dx. You're going to figure out what is the trig function that involves the ratio of the square root term to the constant term. And then you're going to solve for the square root term, and then you'll make the substitutions, and then we'll see what the integral looks like. So I was listening to, they're having a lot of snow over in England right now, and so that's pretty much all they're talking about on the radio. And so I was listening to the radio yesterday, and they came up with two new terms that I'd never heard of before. So one was nesh. You're right, nesh, meaning you're very nesh, or you're nesh. So you'll never guess. So that means somebody who is really sensitive to the cold. So if you're somebody who's like, oh, it's cold, I'm so cold, I need another sweater, then you call them nesh. So that was kind of cool, interesting. That's apparently a Middle English. That's only towards middle of England says that. And it's based on some old English word that sounds like nesh. They were talking to the weather presenter, and the radio presenter said something about her name's Alexandra. Alexander, are you nesh? Yeah, I'm nesh. That's funny. So you can use that next time. And then there was another one So the trig function that always goes, I mean, it's not surprising. Before, sine and cosine kind of go together. So the fact that the trig function involves the ratio of the square root term to the constant term, which is, if you look at your triangle, is the adjacent. This is the adjacent side length. This is the hypotenuse side length. That's the definition of the cosine. Okay. So let's plug it into our original integral. So we get the integral of 5 cosine theta times dx, which is 5 cosine theta d theta, all divided by x, which is 5 sine theta. So we can cancel out 2 of the 5s, and that's it. So we'll get 5 cosine squared theta. This looks familiar. I think. Maybe I'm just imagining things.
You did it as an example.
Oh, did we do? Yeah, it seems familiar. So what did we do? We used the, well, so we don't need to finish it. We'll just say, so what we used was the trig identity. And we ended up with cosecant theta minus sine theta. Okay, let's go to the next one. We already did that one. So this one should look kind of similar to the one we just did, except we have x squared minus 4, which we don't, that means we don't use the sine. So which substitution do we use? What do you think, Elias?
It would be secant.
Secant, yeah. So let's make your triangle. And the definition of the secant is, well, the cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So you want to make the hypotenuse x and the adjacent 5, and that should make the third side x, well, not 5, but 2. That'll make the third side the square root of x squared minus 4. And so I'm going to let you try to remember the derivative of the secant is secant tangent. So that's how you'll get dx. And then you have to figure out what the trig function, once you're drawing the triangle, what the trig function is that involves the square root term divided by the constant term with the triangle as set up. So remember, the secant is the hypotenuse over the adjacent. So x goes on the hypotenuse and 2 goes on the adjacent. And then you can calculate the opposite side from the Pythagorean theorem, which should match the term. So most likely the integral will involve secants and tangents. I don't know how easy it is to solve. I don't remember this problem, so. Yeah, it's supposed to be real windy tomorrow. We got to drive to, after class, we're driving to Alexandria, so hopefully tractor trailer. I'm not worried about me, I'm worried about those tractor trailers getting knocked over. So what kind of integral did you get? Tangent squared theta? Okay. So what do you think you might do with that? Because that's not...
I think I would just use substitution. Oh, actually, power reducing would be better for that.
I don't know what's.
Is there a power reducing?
I don't know. Let's look at the
Yeah.
back of your sheet there.
Yeah, there is.
Yeah,
It's 1
but that
minus
might
cosine.
not. That doesn't look too hopeful because you got cosine. How about what other identities involves tangent squared?
I'm not seeing any right now. Well, this one does, but it's
Yeah, that looks pretty crazy. How about over here?
well, there's this one
Yeah.
with secant minus 1.
Okay. Would that work? Do we know what the integral of secant squared is?
Yeah,
Okay.
it'll be tangent.
Yeah. So that seems like a good option. So the substitutions, you've got x is 2 secant theta because that was based on our original definition substitution. The derivative of the secant is secant tangent. The trig function involves the ratio of the square root to the constant is the opposite side over the adjacent side, which is the tangent. So if we want to solve for the square root term, we multiply both sides by 2. So we get that. So plugging in for the square root of x squared minus 4, we have 2 tangent theta. For d theta, we have 2 secant theta tangent theta d theta. And for x, we have 2 secant theta. So there's the unsimplified version. So we can simplify that because there's some things to cancel out. There's the 2, there's the secant, and so what that leaves is 2 times the integral of tangent squared theta d theta. Okay. So first thing you would do is you'd look in the book to see whether there is a integral for that. Is there an integral for tangent squared? No. So then you think about, is there any way that I can use, well, first thing you might jump out at you is anytime you see something with the squared, you might think Pythagorean identity, or you may think power reducing formula. In this case, why isn't the power reducing formula? Well,
Seems to be more complicated.
yeah, the result of the power reducing formula for tangent squared theta is it has cosine in the numerator and the denominator, so that even sounds, that's terrible. So then you think, is there anything else? Which normally you would also think of the Pythagorean identity. So if we replace tangent squared theta with, what did we have replaced it with?
Secant squared minus 1.
Secant squared minus 1. So we'll use the Pythagorean identity to replace the tangent squared with secant squared theta minus 1 d theta. So now we do have the integral of this. What's the integral of secant squared, Elias? Yeah, so the integral of that is tangent, and the integral of d theta is, we did that last time. The integral of d theta is just theta. Okay, so go ahead and integrate that. The tangent of theta, we already know what that is. We've got it over here somewhere. Yeah, tangent of theta is that, so we can use that substitution to replace the tangent theta. And remember what we did with the d theta is we used the arc trig function that corresponded to the original substitution. So we'll take the arc secant of the secant will give us theta. And so the right-hand side will be the arc secant of x over 2. So we get 2 tangent theta minus 2 theta plus c. And over here, if you take the arc secant of the secant of theta, you get theta. On the left-hand side, on the right-hand side, you get the arc secant of x over 2. So we can replace for theta, we can use the arc secant of x over 2. So we get, so the two substitutions back in is we have the tangent of theta, which is this thing, the square root of x squared minus 4 divided by 2. And theta is equal to the arc secant of x divided by 2 plus c. And we could cancel those out. So we get the square root of x squared minus 1 minus 2 arc secant of x over 2 plus c. So that's the answer. Okay, let's go to the next one, which is you have to go back. So this is, which one are we going to substitution we're going to use here? They got the sine, the tangent, or the secant. Yeah, tangent because you're adding stuff together. Now we don't have the square root of x plus 9 plus x squared. We have 9 plus x squared squared. So the substitution that we're going to have to make, we just have to recognize that 9 plus x squared squared is equal to the square root of 9 plus x squared to the 4th power. So we can substitute this, do that, and that's what we'll get. So make your triangle up. The substitution we're going to make is that tangent of theta is equal to x over 3. And you draw your triangle. Tangent is opposite over adjacent. Okay, I'll let you go work on that one. You could actually solve this without using trig substitution. You just let u equal 9 plus x squared, and you'd have u squared in the denominator. And but we're going to use trig substitution instead of u substitution. That's one disadvantage of people who sometimes are tempted to use an online integrator to circumvent the integrity of the learning process. In other words, known as cheating. Because the online integrator, if they use a way that we don't know how to do, then it's kind of obvious that you didn't do it yourself. Also, sometimes if they leave out steps that you can't just, you guys aren't that brilliant to leave out certain steps. I'm not that brilliant to leave out steps. Just like, oh, it's obvious that it goes from here. So anyway, that's why we have to learn it. I'm sure that happens sometimes, but there was a couple of years ago that I had students that they all made the same mistake on like 2 problems. And thinking of the probability of doing the right thing, that's more likely to happen. But to make the same mistake, especially when they sit near each other, so I think they learned their lesson. Or I learned my lesson. I didn't let them sit next to each other next time. And I think we had a problem like that, didn't we? We used one of these previous problems. We used the arc tangent. I mean, not the arc tangent, but we used the tangent substitution. It was the first problem. So if you go back and look at the first problem, you can pretty much find the substitutions that you need. if you get stuck. Yeah, you kind of think trig substitution would be some obscure method that only solves a limited number of problems, but it's amazing how many problems you end up solving using trig substitution. Does everybody understand what was done there? Okay, so now we have to somehow simplify this thing. So let's see what we got. Okay, so there we go. You can see 9 divided by, if you simplify 9 over 81, it's just 1/9. And the secant squared theta in the numerator cancels out with 2 of the secants in the denominator. So we get tangent theta over secant squared theta. So because everything's done in the numerator, I don't think you're going to be able to just use simple, if it was tangent theta secant squared theta d theta, that would be easy because secant squared is the derivative of the tangent. You could make that substitution. You might say, well, I've got secant squared in the denominator, so I could use the Pythagorean identity, but that really doesn't help too much because you go from one term in the denominator to 2 terms in the denominator. It's probably not going to work that well. Anybody have any thoughts on? Yes, Daniel.
So would you be able to, I don't know if you said this, but would you be able to use U substitution of the tangent?
No, because if the secant squared were in the numerator, but if you use this as u, then you'd have du would be secant squared theta d theta, but the secant's in the denominator, so it's in the wrong place to use u substitution. Anybody else have any thoughts about what to do? So this is why in pre-calculus, you learned about trig identities. Okay. At the time, you didn't have any idea of why you needed to be reasonably confident at using trig identities, which also includes just the definition of the trig functions that are not sine and cosines. You know, you've got tangent is sine over cosine, and secant is 1 over cosine. So, um, so that's kind of a hint. Yeah, I think that's what I would try and see what happens. I don't know if it's going to work, but that's usually probably the best choice at this point. If you had secant squared in the numerator and tangent in the denominator, you probably would use the Pythagorean identity to break up the numerator, but breaking up the denominator into two parts is usually not a good strategy. So tangent is sine of theta over cosine theta, and the secant is 1 over the cosine, so that's 1 over cosine squared. And then when you divide by when you have one of these, and that's another reason back in pre-calculus or somewhere, you know, when you end up with terms like this, where you have a fraction divided by another fraction, it's always good to remember what you do is you multiply it by the reciprocal, because I always get confused about, you know, if it's divided here, does I multiply? You know, I have no idea. I always forget. So I've always just tried not to understand and just remember to take the denominator of this 4-part fraction and multiply by the reciprocal. So the reciprocal would be that. So the reciprocal of 1 over the cosine is cosine over 1. Okay, so let's see what happens. So we end up with sine of theta, cosine of theta, d theta. Now that one looks easy, right? That's about the simplest trig. Now we'll use u substitution. So we'll let u equal the sine of theta. Du will be cosine theta d theta. You know, it's an odd power, so we could either use cosine theta as u or sine theta as u. I choose sine theta because the derivative of the sine is the cosine, not the negative. So just gets rid of one of the complicating factors. So what you'll now, so it's kind of I always think this is interesting when you end up using u substitution within trig substitution. So we've got two substitutions here. So u is sine theta, du equals cosine theta d theta. So what will happen is you'll integrate that, and your answer will be in terms of u. Then you need to substitute back in to get it in terms of theta, and then finally you have to go back and put it in terms of x. So you got to do 2 back substitutions. But basically what we did was we went from something we couldn't integrate. Well, actually we could integrate it. That was the case. In this case, it would be a lot easier to do it the other way. Just start with u substitution to start with. But in this case, we'll find out we get the same answer, of course. That's the beauty of math, is that you can do different ways sometimes and get the same answer, even though it seems crazy that you can, going through all these other intermediate. But it's kind of, you know, math trig identities are good for any value of theta. It's not like they're good for just a limited interval. So whatever we do is good for everything. Okay, so what we do is we have, so we'll have 4/9 times the integral of u du, which is 4/9 times u squared over 2 plus c. So that's finally I was able to integrate it, a polynomial, that's in the book. And then you would substitute back in, so you'd get 4/9 u squared, u is sine, so you get sine squared theta over 2 plus c. And then we'd have to go back and remember our original substitution we used was actually was secant. So we don't have the sine substitution, which is what we need, but the sine is going to be the opposite over the hypotenuse. So the opposite is x. The hypotenuse is the square root of 9 plus x squared. So let's write that down. X over the square root of 9 plus x squared. So sine of theta equals x divided by the square root of 9 plus x squared. So now our final answer is going to be 2/9 times x divided by the square root of 9 plus x squared squared. And that's going to be 2x squared divided by 9 times 9 plus x squared. So I just square the numerator and the denominator. I think that's right. I think so. Okay, so then we're done with that sheet. I came up with this is every year I come up with something new. If you remember back in chapter 5, we did these integrals, or we developed these integrals. 1 over the square root of a squared minus u squared was equal to the arc sine of u over a. We had the integral of 1 over a squared plus x squared. I forgot the dx here, or du. I guess it should be u squared du. That was equal to 1 over a times the arc tangent of u over a. And the third integral we had was 1 over the absolute value of u times the square root of u squared minus a squared du was equal to 1 over a times the arc secant of the absolute value of u over a, something like that, plus c. So that's all we were able to do in chapter 5. And that was because we knew what the derivative of the arc sine was 1 over the square root of a squared minus u. We were able to come up with these equations because we derived the derivatives of these 3 arc trig functions. We actually did it for all of the arc trig functions. The question is, what would be the integrals if I switched? Now that I've got trig substitution, I should be able to figure out what the other variations of this are. So we're just going to look at those 3 cases just to see what happens. So I'm going to use this as an example. What's the integral of 1 divided by the square root of x squared minus 16 dx? So I can't use chapter 5 stuff because I don't have, if I had 16 minus x squared, then it would be the arc sine of x over 4. But what I've got is x squared minus 16, so it's the opposite way around. So because I have x squared minus 16, that means that the substitution I'm going to use is the secant of theta equals x over 4. And I draw my triangle. And the secant is the hypotenuse over the adjacent. So this is x, this is 4, hence the third side is x squared minus 16. That's theta. Okay, we just did this, so let's so we get x is equal to 4 secant theta, dx is equal to 4 secant theta, tangent theta, d theta, and the final substitution we use is the square root of x squared minus 16 over 4 is the opposite over the the adjacent, which is the tangent. So we can solve for the square root of x squared minus 16 is equal to 4 times the tangent of theta. Okay. So we just did a problem like that. We just want to see what happens to this integral. So if we make the substitution, we don't have an x, so we don't make that substitution. But we do have dx, which is 4 secant theta tangent theta d theta. And we do have the square root of x squared minus 16, which is 4 tangent theta. So you can see those cancel out. That cancels out. What you're left with is the integral of the secant of theta d theta. So we borrow Elias's sheet here, and the integral of the secant is equal to the natural log, the absolute value of the secant of u plus the tangent of u. So this is the this is equal to the natural log of the absolute value of the secant of u plus the tangent of u plus c. And then we can go back here and use this for secant and use this for tangent. So we get the natural log, the absolute value of the secant, which is x over 4 from here, plus the tangent, which is this part, square root of x squared minus 16 over 4 plus c. So that's the answer. That's the integral of 1 over the square root of x squared minus 16 dx. So now we do know how to do that problem. Now it turns out if we had done section 8 of chapter 5, it talked about hyperbolic trig functions, and you would find out that these solutions relate to hyperbolic trig functions. What they did there was in the section we skipped, is they defined what the hyperbolic trig functions were, and then figured out the derivatives, and then therefore then they could go the other way and say, well, the integral of that is the results like that. So we actually may go back and do that. I've never done this before. We may go back and do section 8 just for the heck of it. But it turns out you can solve. It's for all the other cases that we haven't looked at. The hyperbolic trig functions ultimately involve integrals that are the opposite of the ones that we did work with. Meaning instead of 16 minus x squared, we have x squared minus 16. And the answers usually involve natural logs. Okay, let me give this back to you and I'll get it when I need it. Okay, let's look at the other cases that we didn't know how to do, but now we do know how to do. And I'm going to let you try this one. So what if you wanted the integral of 1 over x squared minus 25 dx? Remember, we know that 1 over x squared plus 25 involves the arctangent. So, but what we have is x squared minus something, which actually is just like this one, right? Except it's not in a square root. So we're going to still use the same substitution, secant theta equal, in this case, x over 5, and I'll draw the picture for you, but then you're going to do the rest of it. So go ahead and do that one. And remember, x squared minus 25 is the square root of x squared minus 25 squared. The purpose of this is just to show you how much stuff we can do with trig substitution that we didn't know how to do earlier. Actually, I did bring my book today. So while you're working on that, I'm going to look up the section we didn't do in chapter 5. Oh, Christian is here. Just noticed. Got some papers for you, including your last test. Not, yeah, test one actually, not the last test. Did you take that yet?
Yeah. Do you have like one of the sheets everybody looks at for like the integrals and stuff? 'Cause I don't have one.
Oh, you don't have one of those? Yeah. I'll bring that tomorrow.
I had one like last.
Yeah, I gave you one, but yeah, you lost it. Hyperbolic functions. Yeah, while you're working on that, I'm going to write down some stuff about hyperbolic trig functions. Oh, I'm using the wrong substitution, aren't I? No, I'm not. I just drew my triangle wrong. Sorry about that. So yeah, when I got to this point, I'm like, oh, something's wrong. Okay, so we just did this in the last problem. You know, x, so secant is hypotenuse over adjacent. So that was why my triangle was wrong initially. The Pythagorean theorem gives us the third side. So you take the derivative of the secant tangent. The trig function involves the square root term over the constant term, which is the opposite length over the hypotenuse, over the adjacent is, that's the tangent. So square root of x squared minus 25 is 5 tangent theta. So the substitutions we make are for dx, we put in 5 secant theta tangent theta d theta, and for x squared minus 25, we put in x squared of x squared minus 25 squared. So we have 5 tangent theta squared. Okay, so then we simplify it. So we'll get we'll end with 1/5 because we have 5 here and we have 5 squared there. And this tangent cancels out with one of those tangents, so we have secant theta over tangent theta d theta. So that kind of looks familiar. Probably rewrite it in terms of the sine and cosine. So let's do that and see what we get. So remember, secant is 1 over cosine. So you get 1 over cosine of theta divided by sine of theta divided by cosine of theta. And we take the reciprocal, so we get 1 over cosine theta times cosine theta over sine theta d theta. Cosines cancel out. And 1 over the sine, so we get 1 over the sine of theta, but that's the cosecant. So we get the integral of the cosecant of theta, d theta, which is, Elias, what's the integral of the cosecant?
The integral of the cosecant is the negative of natural log of cosecant of theta plus cotangent of theta.
So now all we have to do is go back to our triangle, which I'll draw here so I don't have to go back. So remember, our original substitution was using the secant. Secant's hypotenuse over adjacent. So this becomes 25 minus, or x squared minus 25. So the cosecant is the 1 over the sine, so that's it's x. Actually, let's write it down. So the cosecant is 1 over the sine. The sine is opposite over hypotenuse. So the cosecant is hypotenuse over opposite. And so we go to our triangle here. So the cosecant of theta is 5 divided by the square root of x squared minus 25. And the cotangent of theta is the hypotenuse, adjacent over the opposite. Why is that? Because the cotangent is 1 over the tangent. So you don't have to know anything but SOHCAHTOA. So you got tangent is opposite over adjacent. Therefore, cotangent is adjacent over opposite. And therefore, I go to my triangle, and adjacent is 5. So the cotangent of theta is the adjacent, which is 5, divided by the opposite, which is the square root of 25 minus x squared minus 25. So the final answer is negative 1/5 the natural log of the absolute value of x divided by the square root of x squared minus 25 plus 5 divided by the square root of x squared minus 25. And I could combine these two because they have a common denominator. So I'd have the natural log of the absolute value of x plus 5 divided by the square root of x squared minus 25. There's your answer. Okay. So again, luckily, these integrals are in the book, so we don't have to do anything special. So the last thing I'm going to mention today is, so these are the hyperbolic trig functions. So the hyperbolic sine is defined as e to the x minus e to the minus x over 2, and the hyperbolic cosine is defined as e to the x plus e to the minus x over 2. And the hyperbolic tangent is defined by the ratio of the hyperbolic sine to cosine, just like normal tangent is sine over cosine. The hyperbolic secant is 1 over the hyperbolic cosine. The hyperbolic cosecant is 1 over the hyperbolic sine, and the hyperbolic cotangent is 1 over the hyperbolic tangent. Okay, and you're like, why are they doing that? What's the significance of that? Well, one interesting thing is if you define the sine and the cosine, hyperbolic cosines, you'll find out that the derivative with respect to x of the hyperbolic sine is equal to the hyperbolic cosine. And if you take the derivative with respect to x of the hyperbolic cosine, it's equal to minus the hyperbolic sine. So that's one reason, is because the derivative behavior of the hyperbolic trig functions mirror the derivative behavior of the normal trig functions. Now the integrals are not so simple. Well, yeah, the integral of the hyperbolic cosine is, but it turns out if you look in the book, I'm just going to show you the result here for right now. When you deal with the inverse hyperbolic trig functions, okay, so it turns out that and I'll explain more later. This is just to show you something. The inverse hyperbolic cosine of x is equal to the natural log of x plus the square root of x squared plus 1. So that looks nothing like sines and cosines. But if you go back to the integral we just did a minute ago, like this thing. So when we integrated 1 over the square root of x squared minus 16, we ended up with the natural log of x over 4 plus the square root of x squared minus 16 over 4. If you look at the definition of the inverse hyperbolic trig function, it looks very similar, doesn't it? X plus the square root of x squared plus 1. Okay, so that's not a coincidence. So what they did in chapter 5 is they came up with all these relationships between all these different hyperbolic functions, and they figured out what the derivative of things were, so then they could use the integral. But you can solve the same kinds of problems using